Good morning everyone. I am Mr. Rish. Thank you for joining me for this video. I have been talking quite a bit about limits in the very recent past. Then we talked a little bit about derivatives. And I know I've presented a video on LHopitals Rule. Some books put an S over here, some do not. It depends on the author based on how they spelled it. I might have painted a very rosy picture when it came to LHopitals Rule because there's quite a bit of constraints or restraints that are involved when you're using this rule, though there are also quite a bit of flexibilities and ease which comes by the application of the rule, especially when we're talking about indeterminate forms. Now, what is an indeterminate form? You know, indeterminate means something which lacks a determined value, a determined form, something which has no definite or defined value. Anything of that dubious nature is then mathematically called an indeterminate form. And the best way to explain what an indeterminate form is by means of this example visually. You know, if you were looking at this limit as x approached 1 with regards to this rational function, if you were to just simply put 1 in these areas of x's, you'd get a natural log of 1, you know, which zeroes out, because there's an x-intercept at 1 comma 0 for the natural log function without any form of translation to it. And then if you put 1 minus 1 over here, you get a 0. You're basically getting a 0 over 0. You could technically do right and left-sided limits to get to a good value. From the right side, you could come up with an approximated value of 1.001. From the left side, you could probably use 0.9999. And if you were to use any of these values very quickly for the nature of this video and how we're going to be talking about complex issues, let's just run through this using the right side. If you put the right side limit, approximated value of 1.001, our limit, what we get eventually, a value so close but not exactly, I'm getting this. That such you could say that your limit for this function as x approached 1 would actually be 1. Your function would approach 1. That right here would be an answer. But then when we were talking about this specific rule, LHopitals Rule, in that one video where I devoted specifically time to this rule, you could have done the derivative over here. You would do the derivative of the numerator and you would do natural log x, and you could plug in that 1 over here. Then you do the derivative of the denominator aspect of the function, and you could plug in x equals 1 over here. This would become 1 over x, this would become 1. When you would do 1 over x over 1, you'd get 1 over x, you'd get 1 over 1, and you'd get 1. It would confirm this. But what exactly is an indeterminate form? It's a form with regards to limit is indeterminate if you do not have a clearly defined value. And these are the types of forms which I'm talking about. With regards to the LHopitals Rule application, anytime you're seeing a 0 over 0 play out, or you can say a plus or minus infinity or plus and minus infinity, these are all conventions or terminology I've shown you. This is of the indeterminate form 0 divided by 0. This is here of the indeterminate form infinity divided by infinity. So when you're seeing these are indeterminate forms. Normally when it comes to indeterminate forms, you can get away with using this rule or some modification of this rule. You can sometimes get away with using this right and left side approximations, but usually for the other types of techniques which you might be reliant on, then you wouldn't get away with them, especially for these types of indeterminate forms. And an important rule to remember is for a specific rational function limit determination, if the LHopitals Rule is applicable, you can use the LHopitals Rule and get a good answer. If for a specific rational function, if the rule is not supposed to be used and you end up using it, then you'll end up getting a wrong answer. So what I'm saying is this, perhaps in a very generalized manner, you can think of it as this. For most general functions, you should not be using LHopitals Rule unless there's a clear indication that you should use it. Because if you do this rule for arbitrarily for any kind of function, you can end up getting wrong answers. Let's just spend a little bit of time on these indeterminate forms. For any function which is a rational function as x approaches a, if you find that the f function is approaching a 0 and the g function is approaching a 0, we have the indeterminate. And this is basically terminology you should know because you could see it in paper or on writing, and you would have to be familiar with it. We have the indeterminate type of 0 over 0. This right here is what I'm talking about. If as x is approaching a given value, you're getting a 0 in the numerator function and 0 in the denominator function, you're dealing with this specific type of a indeterminate. It's a form of indeterminate. This is an indeterminate form type of 0 divided by 0. If you notice that for a given function, your value is approaching for f of x infinity. Likewise, you can say the same thing for minus infinity. Here we're talking about indeterminate form type of infinity divided by infinity. Here you can use both positive and minus values and you would be right to do so. Anyhow, for these types of forms, when you're dealing with questions with this, a limit may exist or it may not exist, or a limit might exist that you have some sort of finite form in between. That discussion of whether a limit exists or does not exist is the actual calculation part of the limit that you do when you're using the LHopitals rule or any other technique that you choose to apply. But these right here are not the only forms of indeterminates. You can have several other combinations of indeterminate forms. You can have such conditions play out that there's a tug of war between the indeterminate form where f of x is approaching some value and g of x are approaching some value and they're not the same. You see in these two form types I'm showing you, f of x is approaching 0 and 0, g of x is approaching 0, and f and g of x are approaching the same. So there's no like conflict here between which form for each of these, what the end result is of the individual limits, because there's no conflict here, because both the f of x and g of x are approaching the same values in this top scenario and they're approaching the same value in the lower scenario. But there are some scenarios where there's a tug of war, because in the numerator you might be approaching a 0, in the denominator you might be approaching an infinity. And not only that, in rational functions you can have situations play out, and I'll talk about all of this in this video, where you can have the product of the rational functions approaching different indeterminate forms, and you can have a tug of war between that, or you can have a difference of these indeterminate forms. So there are quite a few scenarios that can play out. Let's very quickly look at what the essence of this rule is. It says as one of the most important defining premises of this rule is that the limit of the quotient, you know what the quotient is, like the division of two items, and we can say limit of the quotient of two functions, and let's just say in this form, limit of the quotient of f of x and g of x, because you know this right here is a rational function. For this specific rule, the limit of the quotient of two functions, f of x divided by g of x, is equal to limit of the quotient, and you know here again quotient means dividing two items, quotient of their derivatives, and that right there is the basic essence of the LHopitals rule, which is why in the procedure for the LHopitals rule you're doing basically running it in this form, right? You're doing that and you're doing the derivative of the base of the denominator function, and then you're able to put in whatever value is over here. So the limit of the quotient of the rational function of the quotient of the two functions, which is a rational function, is equal to limit of the quotient of their derivatives. That's perhaps the most important aspect of this LHopitals rule. This specific rule is not just valid for the general type of limit where x is approaching a given value from both the right and the left side, meaning only that you can apply it for those situations where both the right side and the left side limits are the same. You can apply the LHopitals rule to one-sided limits. That's one of most important flexible nature of the LHopitals rule. You can apply to one-sided limits, where on one side you're getting a specific value, but on the other side you're not getting the same value and it's undefined. But you can apply to one-sided limits. You can apply to one-sided limits for any type of value as x is approaching a. And this is what I'm talking about. X can be approaching a from the right, x can be approaching a from the left, x can be approaching infinity from the right, x can be approaching infinity from the left. And you can also look at it in these forms right here. X can be approaching minus infinity from the right, x can be approaching minus infinity from the left. These are all examples of one-sided limits where x is approaching a given value and it's one-sided, but you can get away with using the LHopitals rule. Perhaps a very important aspect of the LHopitals rule, which I never presented to you in the previous video specifically on this rule, is the fact that when you're doing the derivative of a rational function, the f function and the g function, you can keep running the derivative as needed until the variable is consumed. The examples I presented were able to be solved in terms of the limit of that function, because after only a single round of derivative we were able to come up with an answer. Sometimes you can have questions or functions such that when you do the first round of this derivation process and you want to run your value here through, you cannot come up with a good answer because you still have variables present that are leading to indeterminate forms. You may have to run the whole derivative process twice, 3 times, or you may even have to rearrange your functions as you're running your derivative processes or your procedures, so that you can in the end come up with an answer. Let me show you some of these peculiarities that come into play. Now if you were to look at this question over here, and we're talking about some of these peculiarities that can come into play for the LHopitals rule. If you were to very quickly apply this infinity over here, what would you be getting? You'd be getting e to the infinity, which would get infinity. In the denominator, you'd be getting square, which would be replaced by infinity, square, which would be infinity. So you're basically having the indeterminate form of infinity or infinity. That's an indeterminate form right there. It won't give you a defined value because infinities are not defined values. That's why it's an indeterminate form. You will unable to be able to arrive at a determined form or a defined mathematical value if you run with this over here. You just cannot. And then you are forced to use the derivative rule over here. Based on this rule that we've been talking about, you do derivative of the numerator and you do derivative of the denominator, and then you could put this value in and see how it would play out. If you did the derivative, you get e to the x, and here you get 2x. But you see here, you're still ending up with an issue here where the variable is not consumed. You could do another round if you wanted, another round of derivatives. And let's do another round of derivatives. E to the x in the numerator, derivative of that, and you do derivative of 2x. And now you can see what would happen with infinity. When you did the derivative of this, you get e to the x in the numerator. Here in the denominator, you get 2. Now you can run x to the infinity over here. You'll get e to the infinity divided by 2, and your final answer would be infinity. It's nothing wrong with you getting the infinity. The peculiarity over here I'm showing you was you can run through another round of derivatives if needed, just to consume your variable, so you can more confidently or comfortably say that this indeed is your value. Because here, from here, if you did your actual valuation, you'd still say, yeah, we're coming up with infinity, but you might have been a little less confident about it. But here, with the fact that there's a variable consumed here, now you clearly say, yes, I'm confident that this indeed is the answer. Remember, right now, up till these few examples, I'm still showing you some of the peculiarities of the LHopitals rule. I still haven't shown you those varieties of indeterminate forms that can arise. We will look at that before we actually look at examples, so do not worry. When you're looking at this very roughly, if you plug in zeros over here, you get a 0 in the numerator and you get 0 in the denominator. So you know you have the indeterminate form of this type, 0 divided by 0. It's an indeterminate form type. It's a type of the forms. Derivative procedures over here, you do tan x minus x. The peculiarity over here is the new peculiarity that I'm talking to you about, is that you can run derivative procedures again and again as needed until you are satisfied that you don't want to run them anymore, or you're satisfied to the point that you can come up with a good answer. When you run the derivative procedure here, you get secant square x minus 1, and here in the denominator you get 3x squared, and you could technically say we can put in 0. But look over here, if you're putting in zeros here, you'll get divided by 0. You'll still get undefined, so you're not really satisfied. So you decide, let's run another derivative procedure, and you can. If you run another derivative procedure, you'll have to do the chain rule over here, because now you're going to be running a derivative of a composite. You'll have in the numerator d over du, u squared, and then du over dx, secant x. Derivative of a constant is 0, so don't even bring that up. Here you'll have derivative of this 3x squared, and you could in the end run x equals 0. Let's look over here. You'll have 2u, u was secant x, you know, u was secant x, and secant x is secant x tan x. That's the derivative of that, divided by 6x. So what am I getting over here? I'm getting 2 secant square x tan x over 6x. Now, are we satisfied, or should we run another round of derivatives? If we chose to run another round of derivatives, we could. But the only problem is, well, maybe perhaps not a problem, but you'll definitely, with another round of derivatives, lose this variable in the denominator. But you'll end up dealing here with a product rule and a chain rule, and it might get quite complicated. Your other aspect is if you get tired of running derivatives and you want to say, let's settle down and like come up with an answer, we can. What you have to end up doing is you have to try running with what you have and try to change the form such that you can determine the derivative. And you would write it exactly as how the question is worded, limit x approaches 0, and you'll start separating these things out. The first separation I want to do is 2 over 6. What is 2 divided by 6? It's 1 over 3. Then I want to separate secant square x from everything. I can write again here a new limit x is approaching 0. I'm separating this compound or composite rational function into its individual components, each with their own limits. The thing I want to separate next is secant square x. That's fine, I've done that. Now let's create another separation over here with what it remains. Tan x over x, right? We can do that. Now look over here. If I were to run x equals 0 over here, we're good over here. We're good over here because cosine of 0 is a value. Therefore, the reciprocal of that would be a valid value, a legitimate value. But when we come over here, we'll do tan of 0 and x of 0. We'll get an indeterminate form. So what we can do is run individually this through a derivative procedure. When we run this through a derivative procedure, we get secant square x over 1, right? Don't we? Secant square x over 1. Because we're not worrying here about the quotient rule. We're running it separately. As you know, we will do d over dx tan x, right? Separately. And then we'll do d over dx x. When you do that, you get secant square x over 1. Now we can combine all of this together in a new expression with their individual limits. Limit x approaches 0. We still have this 1 over 3. Limit x approaches 0. We still have this secant square x. And then now we have this limit x approaches 0. We now have this new expression secant square x. For all of these, if we put zeros, we'll get a 1 over 3 over here. 1 over 3 here. We'll get a 1 here. If you put 0 in this, you get 1 over cosine square of 0, which is 1 over 1. You'll get a 1 over here. You're essentially getting 1 over 3 times 1, and your final limit answer is 1 over 3, and that would be your answer. So the limit of this function as x approaches 0, this entire function will approach 1 over 3. Yes, we use the LHopitals rule, but we've never shown you examples of LHopitals rules with this form of elaboration to it. But you can have this type of elaborated LHopitals process where you can run derivative upon derivative to keep simplifying, and then you can separate based on the properties of limits. You can separate your end expression such that you can come up with a clear answer. So let's start talking about some other indeterminate form types. You know, I've talked about 0 divided by 0 or positive minus infinity over positive minus infinity, the types which you have seen with regards to the rule application. But you can have other forms. Sure, if there's a specific function limit as x approaches a, your f of x is becoming 0. You can have a g of x. If you were to put the a value in here and run the limit, you're getting a positive or minus infinity. Now you have a confusing situation here, having an indeterminate form type. This form type is basically designated as 0 infinity, and you can have a positive or minus 0 infinity type. And we're talking about here the products, which is right here. You can have an indeterminate form type of 0 multiplying by a positive or minus infinity, because the f of x for a function, let's say if we have a function like this, the f of x and the g of x, right? This one is generating a limit value of 0 as x approaches a, and this one is generating a positive or minus infinity. Then you have this situation arising. So there's a way of dealing with that, and this type of situation is called an indeterminate form type, 0 times positive or minus infinity. The way of dealing with that is this. You can convert your function, which is a product of two functions, into this type of situation where you can do f over 1 over j. You can convert it into a quotient or a rational function. Or you can say the fg, the product of the two functions, if you were to run that limit through, is equal to also this. It just depends on which form you want to use. And then for each of these forms here, the new forms, you would run the derivative procedure and you'd come up with your limit. And this is best explained to you by means of an example. The point I'm making here is this: if your original function is a product of two functions and you were to run this condition through, and you're having now a tug of war where you're getting 0 as 1, the f of x is approaching a 0, g of x is approaching positive or minus infinity, and you have this form type 0 times positive minus infinity, then you can rewrite this function over here into this form, into a quotient form, and then run the derivative procedure through. And you know the derivative procedure is the LHopitals Rule, and then you can come up with your answer. If you recall, not too long ago I said the LHopitals Rule is flexible enough that you don't use it only for two-sided limits, you can use it for one-sided limits. And I showed you some of those scenarios over here where those one-sided limits, as x was approaching those one-sided values, here's an example of that. X is approaching 0 from the right, and you know here you don't have a rational function in terms of the quotient of two functions. You have a rational function because it's still over 1, but it's a product of two functions. This can be my f function and the g function. Very roughly, if you were to put these values over here, if you look at the graph of the natural log x, it looks something like this. This right here is 1 comma 0. On this side is approaching positive infinity, and it's dipping right here towards minus infinity. If you were to put 0 over here, the f function is approaching 0 as x is approaching 0 from the right, and as x is approaching 0 from the right, the g function, which here's my f function, here's my g function, the g function is approaching minus infinity. Now you have of the indeterminate form type, which I just mentioned right not too far ago. It's of this type, 0 dot minus infinity. This is the type we're dealing with. Indeterminate form type 0 dot multiplying minus infinity. Now we have to decide which of these two forms wins, or what can be our true answer over here. There's a tug of war. And then I said if this type of situation arises, you can convert your function type into a quotient function, f over 1 over g, or you can do g over 1 over f, and then you'll run the derivative procedure. You don't have to do both of these. They'll both, if you can pick this scenario or you can pick this scenario, and they'll both lead you to the right answer. You don't have to run them both. For your own practice you can, but you don't have to in real life. You just pick which of these scenarios you want to use and you run with that. This is my f right here, and this is my g, and let's just go with this first scenario right over here, f over g. I'll rewrite everything as this limit as x approaches 0 from the right, x approaching 0 from the right-sided values, and it's going to be x over 1 over natural log x, right? Now I'm going to do the individual derivatives of this, and that's how we're going to run it. When you do the derivative of x, and you do the derivative of 1 over ln x, you can run it through, and then you can put in your value over here. And perhaps I might have been better off using this, because now I have a quotient rule. Had I done g over 1 over f, I would have had something so much easier. I would have natural log x on the top, but now I have to run with what I chose. When I do the derivative of x, I get a 1 on the top. When I do the derivative of 1 over natural log x, I have to do the quotient rule over here. I have the natural log x multiplying by the derivative of 1 minus 1 multiplying by the derivative of natural log x divided by natural log x square. Alright, you have in the numerator still 1. Now you got to run all of this. This zeroes out because the derivative of a constant is 0. Here you get minus 1 over x. Here we get natural log x square. So over here what we end up getting is 1 over minus 1 over x natural log x square. When you flip everything around, you get minus natural log x square x over 1. You can do the algebra here on the side and it'll confirm that I'm actually right over here, and I am right. And when you've done all of this, you can actually put x is equal to 0. When you run this x value through of 0, you get an eventual answer of 0. But by convention, when you're doing this, you're converting this form by means of this whole procedure into this form right over here, 0 over 0. That's your goal. When you're seeing this, you're trying to convert it into this indeterminate form, from a more complicated, confusing form type to a less complicated, confusing form type, even though they're both indeterminate, but you're going for the better indeterminate. And sometimes you have to be smart and you have to pick the form type which will lead you to an easier process. I picked the form type here which led me to a more difficult process. What would have happened if I had done g over 1 over f? I probably would have been better off, and let's just actually run that through. See what happens. You should always pick that scenario which will lead you to a more simpler response. If I do g over 1 over f, g would be natural log x over 1 over x. Now you're doing the derivative of all of this. when you do the derivative of the natural log x, and you know at the end you'll be able to plug in 0. If you're doing the derivative of natural log x, you get 1 over x. When you're doing the derivative of 1 over x, this is like saying the derivative of x to the minus 1. So let's do that. You're getting 1 over x in the top, and this becomes minus 1 over x squared. When you flip everything around, you get 1 over x times minus x squared over 1. You end up getting a minus x. See, this x cancels out with that exponent 2, you get a minus x. When you put here x equals 0, you get a minus 0, which is 0. So if you had gone with this second scenario right over here, you would have been better off, and it would have been a much easier process. You should always pick that procedure, which will be the easier way. I initially picked this, which was the harder way, but I still got the same right answer. Let's look at this one. If supposedly we were to look at this, here's my f function right over here, and the g function, we have a product of two functions over here. If you were to run minus infinity into x, x would be approaching minus infinity over here, and the g function would be e to the minus infinity, which would be 1, or e to the infinity, which would be 0. You see here now we have the indeterminate form type. You can still say it's 0 dot minus infinity. Order does not matter when you're multiplying, but we have this indeterminate form type. We want to be looking normally at 0 over 0, or plus and minus infinity divided by plus and minus infinity. We want to be looking at these type of form types because they're less confusing and more easy to deal with versus these more confusing types of indeterminate forms. But we have a confusing type of indeterminate form, so we want to be looking at that procedure where you can rewrite the product of these two separate functions as either this f over 1 over g, or you can do g over 1 over f, and then run the LHopitals rule using the value you know. It's just a matter of guesswork which option here I'll apply. I'll go with probably this one right over here. So using this template over here, we run it through. We're doing the derivative of this x, and we're doing the derivative of this 1 over e to the x. And before you even run this derivative, you can usually sometimes just simplify it. Instead of doing the quotient rule over here, you can just simplify this expression and then run that simplified expression through the quotient, through the derivative procedure. 1 over e to the x is the same thing as doing e to the minus x. You don't have to look at a quotient rule over here. You can look at it in this way, and then when you're doing the derivatives of these, you know at the end you'll be able to put x is equal to minus infinity. Anyhow, this will become minus e to the minus x. So basically what are you going to get when you put x is equal to minus infinity over here? Minus infinity will become positive infinity. You get minus 1 over e to the positive infinity. Anything, no matter if it's positive or minus, divided by something so extremely large, it'll zero out, and 0 will be your final answer. Remember, I'm still now showing you the various indeterminate form types that can show up. We're still laying the foundation for the actual questions we'll be looking at in the later part of this video. If a limit x approaches a, the f function is approaching infinity and the g function is approaching infinity. For a function which looks like this, a difference of two functions, we have an indeterminate form type over here, and this indeterminate is going to be called this indeterminate form type. These are the various form types which confuse the whole limit determination procedures. We're basically looking at indeterminate form type, infinity minus infinity. That's a form type. And what are we talking about here? We're talking about differences over here. Indeterminate differences involving this type of function form where you're having a negative, you're having a difference of two functions. The previous one was a product of two functions. Here we're seeing the difference of functions, and this leads to this form type, infinity minus infinity. When you have this infinity minus infinity, you have to run a specific type of procedure just to make the whole function question easier so that you can do the basic procedures that you do know. So in this type of situation here, what's the conflict which arises? If f of x is winning, you're going to get a positive infinity. If you went with the f of x value, if g of x value would be winning, you'd be using minus infinity. You see this minus, it would compound with this infinity, make it minus infinity. So there's a tug of war over here between whether the infinity will be the dominant value or minus infinity will be the dominant value, or will it be some value in between. So how do we go about dealing with this type of confusing situation? Well, we try to convert it again into a quotient of two functions. Quotient of functions, let's just say quotient of functions such that you can have a 0 over 0 form play out, because that's easier to deal with, or you can have infinity or infinity, these type of forms. You want to convert this indeterminate form into something which looks like this indeterminate form, because this indeterminate form is more easy to deal with. Functions which are in the quotient form are more easier to deal with than when they are in difference forms or in the product forms. So when we're talking about these indeterminate differences of this type, infinity minus infinity, we know we're dealing with a question which looked like this in terms of the expression. The main expression was a difference of two separate aspects or two separate functions, and this was generating this form of indeterminate type. And I told you the procedure for handling this type of issue, because this leads to a good amount of conflict between the f and the g, like a quite of a dubious of an issue in terms of solving a limit. You want to convert it into this type of a quotient of the two limits, because when you do this type of change, you're bringing this indeterminate form type 0 over 0, or you're doing positive and minus infinity or positive and minus infinity, which are much easier to handle and evaluate in terms of limits versus this. I haven't told you how we would actually do this procedure, and the procedure is done by three means. One you can do is by means of a common denominator, if supposedly you were able to proceed in such a manner, and you'll see something like that play out in an example I'll show you very soon. The other means you can do it by some form of factoring technique, and factoring, as you know, can also involve isolating. Isolating is a very powerful, or isolation of a common variable. Common denominator factoring, isolation. Another way you can somehow get a difference converted into quotient is by means of some type of rationalizing process. Rationalization. So these are the three types of techniques, and they're not the only techniques, but these are the most commonly employed techniques that you have to depend on for this conversion process. When we're looking at this question right here, limit as x approaches 90 from the left, secant x minus tan x. You know, these secant x and tan x graphs have vertical asymptotes. If you remember specifically, pi over 2 creates an asymptote, vertical asymptote for both of these. So you have a situation here, if this is my f function and this is my g function, the f function is approaching infinity, and you know the g function is approaching infinity, but here we have this indeterminate form of infinity minus infinity, and we don't like that. We want to do is somehow convert this into a irrational function. So what can we do? We can look at this in terms of its base functions. You can rewrite everything as this: limit as x approaches pi over 2 from the left, you really have a 1 over cosine x minus sine x over cosine x. You can do this basically simplification over here, common denominator and all of that. You get 1 minus sine x divided by cosine x, right? If you do this entire expression by algebra, you can convert it into this. Now if you run the derivative of this, you can do this individually. Numerator 1 minus sine x numerator, and the derivative of the denominator cosine x. In the end, you'll be able to put x is equal to pi over 2 and see what would happen. 1 minus sine x, derivative of sine x is a cosine x, but it'll be a minus cosine x because you still have this minus here affecting the derivative of sine x. Derivative of 1 is a 0, so that's useless. Derivative of cosine x is a minus sine x. You can cancel these out. Now you can do x is equal to pi over 2. Cosine of 90 is always 0. Sine of 90 is always a 1. What's your final answer using this procedure? It's a 0. So this right here is going to equal to 0. And we had a peculiarity over here. The peculiarity is this: the indeterminate form of infinity minus infinity. But when you convert it into this other quotient form, it's so much easier to handle, and you can get away with a good answer. Various types of exponential functions where you have a f of x here as the base and g of x here taking the place of an exponent can lead to a variety of indeterminate form types. If in this scenario f of x is approaching 0 or equals 0 and g of x is approaching 0 or equals 0, you have a form type which is called 0 to the 0. And that's a form type which you have to know how to deal with. Likewise, another situation is f of x is becoming or is infinity while g of x is 0. You have this form type, which is again another confusing indeterminate form type. And likewise here, f of x is 1 and g of x can be positive or minus infinity. You have this type of form type, and all of these form types are confusing in terms of determining their limits, the limit of that specific function. How you go about dealing with this type of situation is not very hard. So in these type of situations, you can either manipulate this entire expression by doing the natural log route, or you can convert everything into an exponential route, and then you can run the limit using that. And when you see these in terms of examples, you'll know what I mean. You're basically affecting this in terms of a natural log function, and you're looking at it also in terms of an exponential function. Each of these will lead to different routes, and it will eliminate this type of confusion you would see over here. Anyhow, when you go in either of these routes, I should put an or over here, what ends up happening is you end up converting all of this into this type of indeterminate form type, which is a little more easier to handle than this, or more easier to look at. So you end up converting these types into this type, which is still not the ideal type, but you can get it from a more confusing into a less confusing type. You know, we've provided a method for dealing with indeterminate products, indeterminate differences, and as I've just recently talked about, right before this image, you're seeing the indeterminate powers of these types. If you have a function, as I've already alluded to, which looks something like this, where one function is the base and the other function, the g, you want to call it as the exponent. Your goal over here, as I want to present it or explain it to you a little more clearly, your goal, because any of these types of forms will lead to any of these types of indeterminate dubious powers. You can call them indeterminate powers. You want to convert this into an indeterminate, and that should be your goal. Indeterminate product type. And you know what the product type is, a function of the function which is multiplying, involving the product of the f and the g components. The two subfunctions are in a product form, so you're always then looking at this type of a type. This. Your goal is to convert these types into this type, as I've shown you, and how you will do that. And I showed you two routes, the natural log and the exponential route. And if you think about it, the natural log and the exponential route are not entirely distinctively different. They're not distinct from one another because they're highly dependent on one another. Both the natural log and the exponential applications, being inverses of one another, are usually, this procedure is usually a combination of the two. So you end up doing inherently both of those procedures. If you end up thinking about it in that way, you're not distinctly doing only the natural log or the exponential, you're employing both usually in this conversion from this form into an indeterminate product form. So when you have something which looks like y is equal to, let's use this type of convention, f of x to the g of x, and then you bring in the natural logs, this is what ends up happening. Natural log y is equal to the g of x, the exponent comes as a coefficient, you get g of x, right? And then natural log, and here you'll get the f of x. And you can see now you have an indeterminate product type. One of these will end up being a 0, one of these will end up being an infinity, and you'll convert it into this type. It doesn't matter if it's infinity 0 or 0 infinity, because order does not matter. You can write either or first. Another aspect that can play out is when you're looking right here, if you were to take the natural log on the other side, you can end up showing that y is equal to, you bring the exponential base, then you get g of x natural log f of x, and then you end up having this aspect over here look like the indeterminate product. So just like how this is looking like an indeterminate product type, this is looking like an indeterminate product type, you are eventually converting all of these dubious forms into the less dubious forms, the less difficult or confusing indeterminate product forms or types, which you can better able to answer in terms of determining the limit. So the conclusion when it comes to these types of indeterminate powers is to always make an attempt to convert into this indeterminate product type. It's easier to handle, and just like that previously I mentioned, when you're dealing with the indeterminate product types, there's a method for dealing with that. For the indeterminate difference types, there's a method for dealing with that. And now for the indeterminate power types, there's a method I'm showing you for dealing with that. I'll show you a quick application of this in terms of one or two examples, and we'll get into the actual calculations in this video. Well, you're looking at this function limit as x approaches 0 from the right, x to the power of x. And if you are to substitute 0 in places of x, you'll get 0 to the power of 0, and we are dealing with an indeterminate power type. Indeterminate power types are not good. And you can convert this, actually you have to convert this into a product type by using either natural log or the exponential function. If you're looking at this function, y is equal to x to the power of x, and you know the product types will convert something like this into something which looks like this. This right here is favorable, this right here is not favorable. You use the natural log or the exponential properties to make that conversion. Bring in the natural log and get rid of this exponent. Natural log y is equal to x natural log x. Here we have a product type coming into place. F and a g. You know, with these product types, there's a way of dealing with it. You use one of these quotient types. You can do f divided by 1 over g, or you can do g divided by 1 over f, and we saw something like this is similar to this, or perhaps exactly. And let's go with this. If this is my f, this is my g, we have natural log x over 1 over x. Remember this 1 over f, that's 1 over x. You're doing the derivatives of this. When you're doing the derivatives of this, you get 1 over x on the top. Derivative of x to the power minus 1 is minus 1 over x squared. When you algebraically simplify all of this, you'll get minus x. When you put 0 here in place of minus x, you'll get 0. But you don't think your question is done, because it isn't. Because when you come back over here to this expression, which shows the indeterminate product types, x natural log x is a product type, you still have natural log y. Natural log y is equal to 0. When you solve for y, you have to bring the natural log on the other side by means of this exponential base, and you get e to the power 0, which you know is equal to 1. So this right here, limit, now you've shown by converting the power type to a product type, you've established the value of 1, which is your good answer over here. That's the technique you have to do. Your other route over here could have been from this equation right here. You could have solved for y. Y would be equal to e to the x, l, n, x, and proceed with that way. You have an indeterminate product type here. You have a product type here. And this right here is a product type, because if you put zeros in place of this x, natural log x, see, if you put zeros, you get a 0. Natural log of a 0 is a infinity, so you're looking at it already in the type you want to see it. You don't want to see it in power types, you want to see it in this type. But this right here is a better way of doing it. This might be a slightly harder way. Leave the natural log component till the end, then deal with the natural log component based on your easier form, then running it through from right here. If this right over here represents our f function, and this right here represents our g function, if you put 0 on over here, the f function is really approaching, you have 1 plus 0, the 1. And the g function over here, you're doing cotangent of a 0, you're doing cosine or sine of 0, you're approaching an infinity. So we have the type over here, 1 approaching infinity, and that's not good. It's not a good indeterminate form type, because it's not easy to deal with that mentally and physically, or mathematically it's not easy to deal with. The way we solve this type of question going around it is by means of bringing the properties of logarithms. If y is equal to 1 plus sine 4x to the power of cotangent x, by using the property of logarithms, we can make this get out of that form. We'll have natural log y is equal to cotangent x. Remember, the exponent comes here as a coefficient. Then we have natural log of 1 plus sine 4x. We can convert that into a tangent. Natural log y is equal to natural log 1 plus sine 4x. Cotangent x is the same thing as a reciprocal of a tangent x, is it not? And that's exactly what we have over here. We can put this aside over here for a while. I'm saying this natural log y can be pushed aside here for a while. We'll take the derivative of all of this. The derivative of the numerator and the derivative of the denominator. When we do that, we have to do the chain rule here on the top. D over du, ln u, and then du over dx. We have 1 plus sine 4x. 1 plus sine 4x, and we have a composite here. And the derivative of tangent x, you know, is going to be secant square x, right? Let's look over here. We'll have 1 over u, and we have to do the derivative of this. This 1 over u will multiply by, well, the derivative of 1 is just a 0. Derivative of sine 4x will be a chain rule, will be kicking over there. D over dv sine v, and then dv over dx 4x. Sometimes these questions can get complicated over secant square x. What we end up here is a 4 cosine, derivative of sine is a cosine, but it's a 4x, right? We substitute back for v, 4 cosine 4x. What was u? U was 1 plus sine 4x, right? 1 plus sine 4x all over secant square x. And for all of this, we know we can plug in x equals 0. X equals 0. What happens if we actually plug in 0? Because we've done the derivative over here. We can put a 0 in all of these places of x's and see what we end up with over there. In the numerator, we have a cosine of a 0, which is a 1. We'll get a 4 in the numerator. In this part of the denominator of this top item, 1 plus sine 4x is really doing a 1 plus 0, because sine of 0 is a 0, but we get a 1 over here. Secant square x, with x being 0, you get a 1 over here. So you're basically getting a 4. And we're getting here natural log y is equal to a 4, as x approaches 0 from the right. Solve for y. Take the natural log onto the other side. Natural log y equals 4, therefore y is equal to e to the 4. And this right here represents our limit of this function over here as x approaches 0. Using perhaps an elaborate process, but we got it out of this type. And we were able to bring it into the other type, and using the LHopitals derivative rule, and we can come up with a clear value over here, e to the 4. So when it'll come to actually solving the problems we'll show for this video, this is the schematic we should follow where and when it applies. For the determinate forms, these are the definite forms, the easy, everyday, run-of-the-mill kind of limits. You can use the techniques, limits, approximations, values, your calculator, right and left side values. These are the easy ones. Then the type 0 divided by 0 or positive minus infinity divided by positive minus infinity. Slightly more of the common indeterminate types. You can use the LHopitals rule, as you know, and sometimes you have to run that rule 1 or 2 or 3 times as needed to consume the variable to come up with a good answer. Then for the indeterminate product types, where you're getting a 0 multiplied by an infinity in that type of a form, you convert the product type into some sort of a quotient using that template scheme that f divided by 1 or g divided by 1 or f. Then you run the derivative procedure through there, which is an extension of this LHopitals rule. Then for the indeterminate difference types, where you have infinity minus infinity, convert your expression into some sort of a quotient by means of some sort of rationalizing procedure or some common denominator factoring or isolating process, and then you'll run your LHopitals rule from there. Lastly, when you see an indeterminate power of these types, 0 to the power of 0, 1 to the power of infinity, infinity to the power of 0, and these infinities can be positive or minus, you want to convert your indeterminate power type into an indeterminate product type of this form. And then from here, you can run it through the LHopitals rule, as you know, and the procedure by which you'll actually do the conversion will involve some sort of property involving natural log or exponential basis. You've seen that in practice. So these are the things you want to keep in mind as your schematic when you're doing limits, especially when we're talking about indeterminate forms, which are related to these number 2 to 4 are the indeterminate types. The determinate are the definite ones, where you clearly have a defined value that you can easily pick out. So let's go to practice problems and we'll see how all of this plays out. So every question I'm going to show you here will be from my single variable calculus book, textbook. We have limit as x approaches 1, x squared minus 1 divided by x squared minus x, and we have to see how we can do in terms of the techniques we've learned, how we can run through these questions based on those. If you were to plug in 1 in places of these x, you'll get clearly an indeterminate form. You'll get a 0 over a 0. You do 1 minus 1 0, 1 minus 1 0, so you're using the LHopitals rule. But prior to using the LHopitals rule, if possible, you can always simplify your expression to the greatest extent possible and then run the rule. You can look at the top as x minus 1, x plus 1, and you can look at the bottom as x minus 1. You can cancel these out, so you're basically looking at x plus 1 over x. Now if you put in 1s over here, and we find out that this indeterminate form of 0 over 0 was not too indeterminate as it seemingly appeared. And if you remember, I cautioned anyone watching this video that if you can get away, or if you don't really have to use a LHopitals rule, then you shouldn't use it, because you can end up getting a wrong answer. Sometimes you can get lucky and get away with the right answer, but here if we were to actually put 1 over here, we can get away with a good answer. It would be 2 over 1, and our limit would be 2, and we would be done. So you didn't really have to end up even doing a derivative procedure. What would have happened if you had done a derivative procedure using this expression over here? Well, I'll show you. D or dx, x plus 1 over derivative d or dx, x as x is going to become 1. What would you get over here? You'd get 1, and you'd be saying, using the LHopitals rule, that we have an answer of 1 when indeed the answer is 2. This right here is the correct answer, this right here is the wrong answer. So sometimes caution is to be expected or employed when you're looking at questions which seemingly appear to be LHopitals style of indeterminates, but you can get away with something else after you've simplified it. When we look at this question, we're seeing x to the power of 9 minus 1 divided by x to the power of 5 minus 1. It would be very difficult to factor something of this appearance and then try to cancel things out. You can do a rough appearance over here. 1 placed in the top in the numerator gives you a 0, 1 placed in the denominator gives you 0, so we have an indeterminate form. You would be fine over here with using the LHopitals rule, and you can do the derivative procedure over here. The indeterminate form type we're dealing with is this. So you'll do x to the power of 9 minus 1, and you'll do the derivative of x to the power of 5 minus 1, and you would go with that technique. You'd get 9x to the power of 8, and you'd get 5x to the power of 4, okay? And if you want, you can cancel things out over here. You can cancel this x to the 4 and make this x to the 8, x to the 4. So you're basically having 9x to the power of 4 divided by 5. When you do a limit as x approaches 1, you end up getting 9 over 5 as your limit, and that right there is your answer, because you can just plug in, after you've done this derivative procedure, you can actually plug in x is equal to 1 in places of your x's. See, x is equal to 1. When you put 1 in here, you get 9 over 5. So the answer for this limit for this function will be 9 over 5. So remember, for all of these questions we're presenting, you should be asking yourself in your head, are we dealing with a determinate form, which is a regular type of limits that we're accustomed to, or are we dealing with an indeterminate form, where then all of these other techniques of this video come into place? And you can do a quick answer to that question by running your variable too. If you're running your variable through your x value, if you do the pi over 2, which is 90 degrees, cosine of 90 is a 0, sine of 90 is a 1, but you get a 1 minus 1, you get a 0. So we deal here with the indeterminate form. LHopitals rule can be applied over here. You can do the derivative of the numerator, and you can do the derivative procedure of the denominator, and then see how that plays out. This will come out as a minus sine x, because the derivative of cosine is a minus sine. Then this right here, the derivative of this polynomial will be 0 for the 1, and it'll be cosine x for the sine, but you have a minus cosine x. Minus cosine x. When we cancel out those minuses, we get x is approaching, or actually x is actually at 90 degrees. What happens when we plug in 90 over here? We can plug in 90. We're essentially basically looking at now tan x at an x equals pi over 2 value, and these are not by any means absolute values. This right here is just a side bracket. You're looking basically at tan x at pi over 2. If you remember the curve for tangent, you have vertical asymptotes at play, and it always looks something like this. This right here is my pi over 2, but you're approaching pi over 2 from the right. You're not approaching it from the left, so you have to extend over here, find another round of the tangent function, and as the x values are approaching pi over 2 from the right, your function is approaching minus infinity, and that right there is your answer, minus infinity. Minus infinity. Graphically shown, but if you didn't want to graphically run through this, you can plug your 90 over here. You'll get 90 in place of sine x, you'll get 1. Then you plug 90 in place of cosine, you'll get 0. You'll get a situation of 1 over 0, which is undefined. Now, undefined can be represented in terms of an infinity. The only issue you would have if you didn't employ this graphical technique is you wouldn't be able to tell if it was a positive or a minus infinity. But you can, on the side, on your own, if you're familiar with the graphs, you can run it through and see exactly, and you end up with a minus infinity as your answer. When we look over here at this question, limit as x approaches infinity, this function over here, if you put infinity in both of these cases, you'll basically get infinity divided by infinity, this indeterminate form type. You can probably consider doing the LHopitals rule here, and for the numerator and the denominator, you would get 1 over x here in the numerator. Here in the denominator, you get 1 over 2 root x. You know, when you do the derivative of this, you get 1 over 2 root x, and you can just simplify all of this. You'll have 1 over x times 2 root x over 1, because you flipped the denominator, haven't you, right? You flipped it around. When you do the simplification of this, you're basically getting 2 over root x, because root x goes in x root x times, right? And x is equal to infinity. You don't need to run another round of derivatives, because if supposedly you put an infinity here in the denominator, you get such an exceedingly large value in the denominator that you can say that your entire limit or function reaches 0 as x approaches infinity, and you would be done with this question. So we are here dealing with an indeterminate form type of this. This right here will be a question similar to the one we just saw. To determine your indeterminate form type, put zeros in here. You'll get 0 in place of this x, you get 1 minus 1, you'll have a 0 divided by 0. This is the form type we're dealing with. We can do a round of LHopitals Rule and see how that plays out for us, and we'll see from there whether it was beneficial or not. If you do the derivative of all of this, you'll get e to the x in the numerator, and here in the denominator you get 3x squared, and you can do x is equal to 0. You can do another round of derivations if you wanted. In the numerator and denominator, you'd still get e to the x in the numerator, and here you get 6 to the x. So it's not really helping us too much. If you put 0 over here, you're getting some sort of undefined value, whether it's going to be a positive or minus infinity. We can use a calculator here and run like a right or left sided limit. I'll run a right sided limit close to a 0, and I'll use 0.0000. Let's just say I'll use as many can fit in my calculator, and I'll run it through this expression over here and see what we get in terms of our value. If I take all of these zeros and I save them with that last digit 1 into my calculator and I run it over here, what I get is this. I'm getting an exceedingly large number. It was something to the power of a double digit number, and I will say very comfortably that this function will approach infinity. You could have graphed it and you could see that your function will zoom out towards infinity or exceed beyond bounds, but infinity right here is a good value. For this question, limit as x approaches 0, tan hx divided by tan x. If you don't have this function here on your calculator, you cannot very quickly run this through and see what type of form we have. You would have to look at tan hx as sine hx divided by cosine hx, which you would remember as e to the x minus e to the minus x divided by e to the x plus e to the minus x. Remember, the over 2's cancelled out, and you'd run zeros through here, through those x values. If you ran zeros through here, you get 1 minus 1. You'd get a 0 on the numerator, and you'd get a 0 over 2. E to the power of 0 minus e to the power of minus 0 is a 0 divided by e to the power of 0 is a 1 plus 1, 2. You're still getting a 0, but you would get a 0 here in the numerator, and you get tan of 0 as a 0. You get this indeterminate form type 0 over 0. So you know you can run the LHopitals rule if you choose to do so, and I would, and we would see how that plays out. The derivative of tan hx, if I remember correctly, is secant h squared x. The derivative of tan x is a secant square x, and x is equal to 0. I'm just going to look at my reference sheet over here to make sure the derivative of that hyperbolic is correct, and it is. Now you basically have to run the zeros over here, the 0 value in place of this. You know, secant h squared x is the same thing as saying this right over here is the same thing as saying 1 over cosine h squared x, which is the same thing as saying 1 over e to the x plus e to the minus x over 2 square, right? Which is the same thing as saying 4 over e to the x plus e to the minus x square. So we're going to have to plug in the 0 in places of these x's, and secant square x is easy because you know 1 over cosine square x is equal to secant square x, and cosine of 0 is 1, so this one right here will automatically be a 1. We just have to determine what this is when you plug in the 0 value right over here, and we can do that on our calculator. Run the 0 here to the x values in the denominator and divide that from 4. When you do it, you get a 4 over 4. When you run the 0 to here, you get 4 over 4, which is a 1. So you're basically getting a 1 here, and the numerator is giving you a 1, denominator is giving you a 1, so your final answer here is a 1. So this function will approach 1 as x approaches 0. It was not a hard question, but it became hard because my calculator here does not have hyperbolic functions on it. If I had it, I could have very easily calculated this out without having to go through this. This right here is one of those scenarios where you would outrightly jump to the LHopitals rule for application, and it wouldn't be a wise way to go. If you were to look at the graph of a natural log function, you know it looks something like this for the standard natural log. 1 comma 0 is the x-intercept right over here. It's going here in the direction of positive infinity. Here it's dipping down towards the minus infinity, and I'm talking about the curve. If you put 0 here, values of x approaching 0 from the right, just for a rough determination, you get natural log of 0 over 0. You're not getting a clear indeterminate form of a 0 over 0 or an infinity over infinity, whether they're positive or minus infinities, but you're not seeing that. Natural log 0 would be eerily close to a minus infinity. You're basically looking here at a form which is kind of like a minus infinity over 0. It doesn't look at like any of these forms, so you don't want to use LHopitals rule over here at all. I would not recommend it. Just use your basics over here. As you know, values of x as they approach 0 from the right, a good value would be 0.0000, or like squeeze in as many zeros as you can on your calculator screen. and save this value and run it through this function. When you run it through your function over here on the top, you have to use your calculator here. And let's do it. We'll publish a value here shortly in regards to our value for this limit. I'm going to run the value through the natural log and I'll divide it by x minus 2.07 times 10 to the 10. If I were to run in more zeros, I would eventually hit minus infinity, and that right here would represent the limit of this function minus infinity. So don't use the LHopitals rule for something like this when you don't have a clear indeterminate form. It's not like anything what you've seen over here. These are the types which you might see with regards to asymptotes or the basics that you know. So here in these cases, run your approximate values instead, but this minus infinity would be a good answer. This will be the last type of question I will demonstrate for the basic LHopitals form types, the indeterminate form types of 0 divided by 0 or infinity divided by infinity, because I want to get into those indeterminate products or indeterminate differences or the indeterminate power types, which we'll be looking at after this example. But if we were to roughly put zeros over here, we get 5 to the power 0 minus 3 to the power 0, which are 1 minus 1 is a 0 divided by 0. We're looking at this indeterminate product type. And then you can just do the derivatives over here and see how everything plays out in terms of your expression. When you do the derivative of a power function, you're going to get, remember the derivative of b to the x, anything which looks like b to the x is b to the x natural log b. So this will become here on the top 5 to the x natural log 5 minus 3 to the x natural log of 3 divided by derivative of this is just a 1, right? And in this expression you can easily put that 0. When you put the zeros over here in places of the variables, you're getting 5 to the power 0 natural log 5 minus 3 to the power of 0 natural log 3, and you are getting natural log 5 minus natural log 3. If you use your properties of logarithms, you can rewrite this. The difference becomes a quotient of your logs, natural log 5 over 3, and you can come up with a numerical answer over here. You don't have to. You can say this right here is your answer or this right here is your answer. They're both equally good. And then I would just write here natural log 5 over 3. The function as x approaches 0, this function will approach natural log 5 over 3, a numerical value which you can easily determine. So now we will actually get into the substance of the video where we're talking about these other types of indeterminate forms. When you're looking at this question where you're looking at an f and a g and you're thinking about an indeterminate product form. And that's exactly what we have. If you were to put this infinity in places of x, you would technically end up having, well, the f function would be just this infinity, and then this sine pi over x would be sine of such a small number, pi divided by infinity as you plug it in would be essentially saying sine of 0, and you're basically looking at 0 infinity or infinity 0 form. This is the indeterminate product form. Both of these, order does not matter, and you have to proceed with this type of formula that you're going to do the quotient application here, f over 1 over g, or you'll do g over 1 over f. Judgment here to make is which one should we go with, because which derivative will be better handled, with this in the numerator or this in the denominator, and vice versa. I think I'll go with this one, g over 1 over f, because this is my f, this is my g. I'll do the derivative of these. I'll do sine pi over x, and then I'll do derivative over here of 1 over x, right? It's always 1 over. This right here is going to be a composite. You're going to do d over du sine u, and then du over dx pi over x, and this right here, derivative of x to the power minus 1 is a minus 1 over x squared. And sometimes we find out the derivatives are becoming too complicated, then we've probably picked the wrong frame and we should go to the other way then. The derivative of this would be cosine u, the derivative of pi over x. We have to do, now this right here is going to be a little problematic because we have a x here to the power of minus 1. We have to look at it as this. We're doing du over dx of pi to the x to the minus 1. So that's going to bring a different factor over here. We're going to get minus pi over x squared, because this pi can technically come out as a coefficient. So when we're doing the derivative of all of this, we're getting cosine u multiplied by minus pi over x squared, right, over minus 1 over x squared. So now we're committed to this procedure. We have to run it through. So from here, the next step is to simplify all of this in terms of the algebra, involved and resubstitute the u because we have a chain rule in effect over here. Let's put the u aspect back. It was cosine u was pi over x. And this pi over x squared, let's bring the pi coefficient right before the cosine, nothing wrong with that. This over x squared is entirely over all of this. And then we still have this 1 over x squared. We have to deal with that 1 over x squared. You know, when you flip everything around, these x squares will cancel out, but I'll show you pi cosine pi over x. This pi over x is inherently attached to this cosine, but this pi over x squared right here is not attached to the cosine in terms of its angle, because the angle was here enveloped by this u. This right here is a u. This pi over here has come out as a coefficient. You have this over x squared. You have to keep all of this in track, otherwise you can make a silly mistake and your whole question will be ruined. X squares cancel out. You essentially get pi cosine pi over x. This pi over x is the value in terms of the angle for cosine that you're affecting it by. And everything you know here with regards to LHopitals Rule is going to be hit by this infinity, because I haven't been showing you these. Remember, x is equal to infinity? Here you can write x is equal to infinity. I wasn't bringing all of this because it gets kind of busy. Now all you have to do is run this infinity in the variable x. When you run infinity here into this variable x, you're doing pi divided by infinity. Pi divided by such a large number makes the whole number equal to 0 because you make it exceedingly small. You're essentially saying pi cosine of 0. You know cosine of 0 is a 1. 1 is hitting with this pi and giving you a final value of a pi. If you didn't see this, you can say right over here, pi cosine of 0. Cosine of 0 is a 1. 1 times pi is this pi right here, and our answer is done. This question was not tricky because of the indeterminate products at play and this scheme at play. It was perhaps tricky because of the derivative which became involved. There's such a room over here for making a silly mistake that you can end up with a wrong answer. For this question over here, limit as x approaches 0, we have this function over here comprised of two little sub-functions, f and a g. If you were to plug in the 0 values, you'd get a 0 over here and you get an infinity over here. You'd be looking at this type, the indeterminate product form of this. And you know you can't really roll with that because you have to use the quotient aspect. You have to view it as this, f over 1 over g or g over 1 over f. You gotta run it with that form. That way you can bring the proper types, 0 over 0, or you can do infinity or infinity. By using it in that way, you can convert it into this form. And that's how you have to roll with this question. And now the debate becomes, should we make this f or g, or this should be f or g? And that's the tricky part, because if you make the wrong mistake or the wrong choice, you end up with a very difficult derivative to deal with. I'll basically keep this as my f, my g, and I'll roll with this technique over here. So I'm going to be doing the derivative of the sine 6x in the numerator, and then I'll be doing the derivative of, you know, it's 1 over, don't forget the 1 over, cotan 2x. But before you do the actual derivative procedures, you can simplify what you can when you can. This will be sine 6x. You know the reciprocal of cotangent becomes a tangent. This is same as saying tangent. You know the chain rules are going to kick in over here. D over du, sine u, d over dx, 6x. When you do the entire chain rule, you'll get in the top 6 cosine 6x. Chain rule over here. D over dv, tan v, dv over dx. 2x, you'll get 2 secant square 2x, and then you can easily put the 0 in places of x's. Plug in the zeros. You have 6 times cosine of 0 divided by 2 times secant square of 0. You know cosine of 0 is a 1, secant square of 0 is a 1, because reciprocal of cosine is a secant. Whatever values are for cosine will hold in terms of values for secant, especially when we have 0 as our degree angles. You'll get a 6 divided by 2, which will be a 3, and that'll be your final answer. So the limit of this entire function will be 3 as x approaches 0. And we've converted an indeterminate form of this product into the quotient form, and that helped us realize the good answer of 3. If you look at this question as x approaches minus infinity for this product of two functions, we have an indeterminate product form playing here. Because if you do minus infinity squared, you'll get an infinity. If you do e to the power of minus infinity, you'll get 0, and you have a 0, infinity, form, this type form. You want to use this technique over here, f divided by 1 over g, or g divided by 1 over f, to make this into a more manageable form, something which looks like this. That's what we're trying to do over here. The question over here will be, what will we run through in terms of the numerator derivative and the denominator derivative? It shouldn't be too hard of a guess. Sometimes it's trial and error to determine which one you want to do in the numerator, which one you want to do in the denominator, whether you want to pick this or this. I'll keep the x squared in the numerator. Let's do x squared over here. Here's my f, here's my g. We'll go with this one right over here, this template here. Then in the denominator, I'm doing d over dx, 1 over e to the x. We can rewrite everything as this, x squared, and we're doing the derivative of e to the minus x. The derivative of x squared is 2x. The derivative of e to the minus x is minus e to the minus x using the template. Let's run this through another round of derivatives. In the numerator and denominator, we'll get a 2 in the numerator. Derivative of 2x is a 2. Remember, you can run the derivative via the LHopitals Rule several times as needed. Derivative of minus e to the minus x will be, minus will multiply with that minus, will get positive e to the minus x. And you know, we could eventually put minus infinity over here. We're basically going to end up doing this 2 over e to the minus infinity, because we can actually plug in minus infinity, which is saying that's 2 over e to the positive infinity, an exceedingly large number in the denominator, making the whole value so small that you can say your limit approaches or your function approaches 0, and this right here would be your good answer. When you're looking at this question and you're thinking about plugging in zeros into these products over here, you get a sign of a 0 and you get a natural log of a 0. You're looking at this product form type, an indeterminate product form type, and you know you have to do some sort of quotient procedure which looks something like this or something like this. Whenever you see this type of form, you want to be thinking about these types of procedures over here. The debate here is which one should we run through, this or this. Here's my f, here's my g. I'll go with this one right over here. I'll keep the natural log on the top, d over dx, natural log x over d over dx. Never forget that here, this is a reciprocal you have to run. It's 1 over f or 1 over g. And sine x, you can rewrite this again in a better way, because the reciprocal of sine x is basically cosecant x, right? Cosecant x, and all of this allow you to put 0. Derivative of natural log x is 1 over x. Derivative of cosecant x is minus cosecant x cotangent x. Okay? Minus cosecant x cotangent x. Now when I come over here and I'm trying to put in an x equals 0, what am I end up getting? 1 over 0 here in the numerator, and here in the denominator I'm getting minus cosecant 0 and cotangent 0, which are not favorable. And I realize that I'm using the wrong template. I should have ideally used this. So I'm going to switch gears and use that. And there's nothing wrong with you doing this trial and error procedure, because this procedure here didn't help me out. I will do this now. D over dx, I'll put sine x in the top. Sine x. Remember, I'm going to follow this scheme, f over 1 over g, and then d over dx, 1 over natural log x. The derivative of sine x is a cosine x. The derivative of 1 over natural log x, you have to end up using over here. You have to end up using over here that quotient rule over here. You're going to get the quotient rule at play. You'll have natural log x times the derivative of 1 minus 1 times the derivative of natural log x over natural log x squared. What do we get? Cosine x over, this 0 is out because derivative of is a 0. You essentially get here a minus 1 over x divided by natural log x squared. You can flip everything around. You get a cosine x times natural log x squared divided by minus 1 over x. When you flip this around, this minus 1 over x can flip around such that the x will attach right here in the numerator, bringing the minus with it. You get a minus here and then the x comes over here, and you're plugging in your x equals 0. Cosine of 0 is a 1, but natural log of that 0 is undefined, but the 0 affects here in terms of the x, and you get a 0, and everything zeroes out eventually in the end. And that ends up being the limit for this question. A bit of a convoluted process here, but you bring 0 into the procedure over here and as your limit. Your function approaches 0 because here 0 will give you a value of 1. Here natural log of 0, you can't do that, but here when you do 0, it zeroes everything out. The minus becomes moot. Let's look at this one over here. It's a product of two functions. If I were to put 1 in over here, in places of these x, I'll get natural log of 1, which is a 0. And tan of a pi over 2 is undefined, infinity. So I have a 0 times infinity type. So I know I have to use a quotient rule over here. I have to do either this. Fg is to become f over 1 over g to make it a quotient, or I have to do g over 1 over f. Now the problem is, which one am I going to do? Here's my f and g. I'll just keep the natural log in the numerator and I'll proceed with that. Natural log x in the numerator, and I'm doing d over dx 1 over tan pi x over 2, which you can rewrite as cotangent because the reciprocal of tangent is cotangent, right? You'll have d over dx here, natural log x, and then this becomes derivative of cotangent pi x over 2. 1 over x here stays in the numerator. In the denominator we have a chain rule over here. We will have d over du cotan u, and then du over dx pi x over 2. All of this will play out such that at the end we can put in 1. In the numerator we're just going to get 1 over x, which is already done. Here we're going to get a minus cosecant square u times the derivative of pi x over 2 is a pi over 2, right? Pi over 2. We'll get a 1 over x here in the numerator, and here we're getting a minus pi over 2 I'm bringing first, and cosecant square u, which was what? Pi over 2, right? Pi over 2. That's what we're getting, and we can in the end put 1s over here. Now we have to play this out, and it's not going to be hard. When we put 1 here in the numerator, we get 1 over 1. That's easy. We're retained with that 1. When we put 1 over here in the denominator, and it should have been a pi x over 2, pi x. Because our original substitution was let u equal pi x over 2, pi x over 2. When you put 1 over here in this, we get a pi over 2. Sine of a pi over 2 is a 1. Cosecant of a pi over 2 is a 1. Square of that 1 is just a 1, and we get a minus pi over 2 here in the denominator. And you can run that through yourself on a sheet of paper for your own knowledge sake, and you'll get as an initial and final answer minus 2 over pi, because this thing flips around and that's what your final answer is, and it should be right. When we're looking at this question here, limit as x approaches infinity x cubed times e to the minus x square, we're dealing with a product of functions. If you were to plug in infinity in places of x's, you'll see very easily you have an infinity and 0, or you can say 0 dot infinity indeterminate product type. And you have to convert this into the quotient form. Fg is equal to f over 1 over g, or g is divided by 1 over f. And this right here is the most hardest part, because you have to make sure you're picking the right items or which framework you're using, because sometimes you can end up on a very difficult path of derivatives. I want to do the derivative such that I'm going to keep the x cubed in the numerator, and then I'll do the derivative of 1 over e to the minus x square. You can rearrange things around to make things easy. Look over here, d over dx is equal to x cubed, and this 1 over x e to the 1 over e to the minus x square can flip around to get rid of that negative exponent. You'll have e to the x square. You're doing the derivative of this. At the end of all of this, you'll actually be able to plug in x is infinity. The derivative of x cubed is 3x squared. The derivative over here using the chain rule would be 2x e to the x squared, and you can see that for yourself. And you can simplify these variables. X's and that x squared can cancel out. You get 3x over 2e to the x squared. This is what I have so far, but I'm not satisfied with what I'm seeing over here, because I still have a variable in the numerator. I want to send this to another round of derivatives, because you can. With the LHopitals rule, you can do as many derivatives rounds as needed until you can come up with a good answer. When I take the derivative of the numerator and the derivative of the denominator, the numerator will just give me a 3. Here in the denominator you have to do the chain rule again, but when you do it, you can do e, u, and then 2x multiplied by that 2, you get 4x e to the x squared, and then you can run this x equals infinity in the end. Remember, u equals x squared, you would have had 2 times e to the u times 2x. Here's what I'm doing in terms of the derivative here of the chain rule. You have gotten 4x e to the x squared. 4x e to the x squared. When you do this assumption here of x is becoming infinity here, you'll get 3 divided by such an exceedingly large number, which will all infinity out, you'll come up with an infinity in the denominator, making your entire numerical value very close to a 0. So the limit of this entire function as it approaches infinity for this product of these two functions will be 0, and that answer will be good. Let's look at this question over here. Limit as x approaches 0 from the right, we have x to the power of x squared. Put in the zeros over here. In place of x, you get 0 to the power of 0. So we know we have this indeterminate power type at play into such a form that you can see the indeterminate products coming into play. And you do that by means of the natural log or the exponential functions. If you view this entire expression as y is equal to x to the power of x squared, you do the natural log y. That enables you to bring this exponent and bring in this. Now you have a products at play, indeterminate products. You know, if you would put 0 over here, you'd have 0 and infinity coming into play, this template. But when you're doing it in this form, you have to do the quotient rule now, right? 1 over g, or you have to do g over 1 over f. It all boils down to this, especially for these indeterminate power types. I will have to decide which I want to keep in the numerator, which in the denominator. I think I'll just we'll roll here with this template right over here. So we have the derivative of the natural log x in the numerator, and then we'll do the derivative of 1 over x squared. The derivative of natural log x is 1 over x. The derivative of x to the minus 2, x to the power of minus 2 will be minus 2 over x cubed. That's what it'll play out to. And then you can flip everything around, times minus x cubed over 2. You basically get minus x squared over 2. When you put 0 in place of this, you end up zeroing it out. But remember, you have to think about this part right here. Natural log y was equal to 0. Y is equal to, take the natural log on the other side, bring in the exponential base e to the power of 0, and that yields you your answer of 1. So the limit of this function right over here, as x approaches 0 from the right, your function will approach 1, and that will be your answer. So this right here was an example of the indeterminate power of this type, 0 to the power of 0. Let's look at this question. Limit as x approaches 0, 1 minus 2x to the power of 1 over x. You know we're dealing here with indeterminate power types. If you were to put 0 here, you would end up getting this form, 1 to the power of infinity, clearly an indeterminate power type. You have to somehow convert this into an indeterminate product type. And you can do that by using this rule right here, where you convert it into quotients. And you have to convert this entire expression into a product formation using your natural logs. Natural log y is equal to 1 over x, natural log 1 minus 2x. Because you can bring the exponent as a coefficient by employing natural logs. Here's your product expression now. You just have to decide which of these is f, which is g, meaning which format will you use. And I believe I will go with this format right over here, keeping the natural log on the top. Derivative of the natural log 1 minus 2x divided by the derivative of 1 over x. My f function is 1 over x. See, 1 over x, but you still have to do the reciprocal of that. When you do the derivative in the numerator, you get d over du, ln u, and then du over dx, 1 minus 2x. Here you're doing basically just the derivative of 1 over x, which is just x. Everything flips to just a single x. Here you get a minus 2 over 1 minus 2x, that's the derivative, and here you get 1. Essentially all you're doing now is you're going to be putting this x equals 0 right in places of x. When you put x equals 0, you get minus 2 divided by 1. Everything else one's out. Because of this denominator 1, you get a minus 2. But this right here was natural log y is equal to minus 2. Y is equal to e to the power of minus 2, and that right here will represent your limit. Limit of this function as x approaches 0 will be e to the power of minus 2. E to the power of minus 2, that will be your answer. When you look at this question here, limit as x approaches infinity for this power function, if you put infinity in places of x, you end up getting infinity to the power of 0. That's the type we're worrying about, and you can do that by viewing your entire function as x to the power of 1 over x. You bring the natural logs. Natural log y is equal to 1 over x, natural log x. This right here is now my function in terms of the products. We're going to view it such that we can convert this. Remember, our goal is to convert it into this type of form, so we can get from this more dubious to the less dubious form. And we're going to do the quotient rule over here. Fg will equal to either f over 1 over g, or it will be g over 1 over f. And I'll keep the natural log x on the top, and I'll go with this one right over here. The derivative of natural log x divided by the derivative of 1 over x. This question does not seem to be too hard. It'll be 1 over x here on the top, and it'll be derivative of x right here in the numerator. Let's not skip a step over here. It'll be derivative of x right over here, and we can be able to put x is equal to infinity. The numerator is done in terms of the derivative. We'll get 1 over x over here. Here we'll get 1, and we can do x is equal to infinity. All you're doing now is putting infinity in place of this x. You're doing 1 over infinity, an item in terms of value so small that you can say it's equal to 0. But this right here is not our final answer, because we have to view it in terms of this. Natural log y was equal to 0. See, natural log y was equal to 0. Therefore, y is equal to e to the power of 0, which is equal to 1. And 1 will be our final answer. This question over here will be slightly more challenging, only in terms of how the function is. If you put zeros in places of x's, you're going to get here 1 to the power of infinity, and this is the indeterminate power type that we are dealing with, this form. We have to use the quotient rule over here to bring it into forms of products. But before we do that, we're going to write everything in this way. Natural log y is equal to cotangent x, natural log 4x plus 1. Here's our products, and this will help us convert this into this type of format. 0 times infinity. We have to view this in terms of the quotients. Fg is equal to f divided by 1 over g, or g divided by 1 over f. I'll keep the natural log here in the numerator, and because that might prove to be beneficial. Natural log 4x plus 1 divided by 1 over cotangent x. 1 over cotangent x can become a tangent x. We'll worry about that in the next step. We have to do the derivatives over here using the chain rule. When we do the chain rule over here, you can probably do this in your head. You'll get a 4 over 4x plus 1. You can do the derivative and you'll get this. And when you do this, you're basically looking at the derivative of tangent x, because the reciprocal of cotangent is tangent, right? You're going to get derivative of tangent x, which is secant square x. And that enables us to put zeros in places of these x's. When you do that, you get 4 over 1 over 1, and you get 4, right? Because this becomes a 1 here, this becomes a 1, so you're doing 4 over 1. But natural log y was equal to 4, therefore y is equal to e to the power of 4, and this e to the power of 4 is our actual answer. The limit of this function will be e to the 4. For this question here, cosine x to the power of 1 over x squared, if you put zeros in places of everything, you'll get a 1 over here. You're basically looking at 1 to the power of infinity type. And you have to convert this into a form of products. Y is equal to cosine x to the power of 1 over x squared. Natural log y is equal to 1 over x squared. Natural log cosine x. And here's my indeterminate form of the products. We can run this through the quotient rule. You know what the quotient rule now is in terms of these limits. It's either f over 1 over g, or g over 1 over f. You can decide which one you want to use. I'll keep the natural log in the numerator. D over dx, natural log cosine x divided by d over dx, 1 over x squared. Because see, this 1 over x squared has to be hit with this 1 reciprocal. Here in the numerator, you can do the chain rule over here. ln u, du, all of that. The cosine u, you'll get a minus sine x over cosine x. That's what you'll get in the numerator. If I've done it properly, that's what you'll get. And then here you'll get the derivative of what will be eventually for x squared, because this flips around. You get a minus tan x over here, and here you get a 2x. And eventually you can put x equals 0 over here. I'm not satisfied with the appearance of this because I want to run this through another round of derivatives. If I run it through another round of derivatives, it can help me out. Minus tan x will become minus secant square x. 2x will become a 2. I can put x equals 0 over here. When I put x equals 0 over here, I get a minus 1 over 2. Minus 1 over 2. And you can see that secant square of 0 is a 1. A minus 1 divided by 2 is a minus 1 over 2. But we know that natural log y was equal to minus 1 over 2. Therefore, y is equal to e to the power of minus 1 over 2. E to the power of minus 1 over 2. And that right here will represent our answer. And we can bring our answer right over here in a more clear form. E to the power of minus 1 over 2 is our final answer. If you want to be fancy, you can rewrite this in this way right over here. 1 over e to the 1 over 2, right? Because this minus brings it as a reciprocal. You can write this even as 1 over root e. These are the different ways of saying the same thing. But it's e to the minus 1 over 2, same thing as 1 over root e. Let's look at this question here. If you put 1 in place of these x values, here you'll get a 1 in the base. Here you'll get an infinity. We have to convert this to an indeterminate product type, and we can do that by employing the natural log technique. Y is equal to 2 minus x to the power of tan pi x over 2. Therefore, natural log y is equal to tan pi x over 2 natural log of 2 minus x. And you know we have to follow one of these schemes now because we have a power form converted into a product form. Either we'll do f over 1 over g, or we'll do g divided by 1 over f. I'll keep the natural log in the numerator and I'll proceed with that. D over dx, natural log 2 minus x divided by d over dx 1 over tan pi x over 2. You can do the chain rule over here and you get minus 1 over 2 minus x. Here you're looking at basically the derivative now cotangent pi x over 2, because that's the reciprocal of this. You can easily manage that. When you do the derivative of this denominator item, you get minus 1 over 2 minus x has already been established for the top, but here you're going to get pi over 2 minus cosecant square pi x over 2. That's what you're going to get. You can work it out and you'll see it. And this is x is approaching 1. All you gotta do now is just put 1s in places of these x's and you'll solve it out. You put 1s here in the numerator, you get minus 1 divided by 2 minus 1, which is minus 1 over 1, minus 1 over 1. Here you put 1s in place of this. Cosecant square of 90 is just a 1, square of that is a 1. Hit that with a minus pi over 2, you get a minus pi over 2. These minuses can cancel out, you get 1 over 1 times 2 over pi, and your answer is 2 over pi. But that is not complete yet because you have to factor in for this part right here. Natural log y is equal to 2 over pi, therefore y is equal to e to the power of 2 over pi, and that right here will be your final answer, e to the power of 2 over pi. And we can write it here again clearly. E to the power of 2 over pi is our function approaching this limit as x is approaching 1. This will be the last question I'll present for the indeterminate power types. If you put infinity in places of these x's, you'll get 1 plus 0, which is just 1 to the power of infinity. So this is the type we're working with, and this is the type you want to convert it into something which looks like this, an indeterminate result of products in the product format. Let's start with y is equal to 1 plus 2 over x to the power of x. Then natural log y is equal to x, natural log 1 plus 2 over x. Here is our form of products. We have to do the quotient rule, as you know. I won't write it out. I'll keep the natural log in the top. I'll do the derivative of this g part. Here's my f part, here's the g part. Natural log 1 plus 2 over x, and the derivative of the f part, which will be 1 over x, as you know. And that will enable us to put x equals infinity somewhere down the road. When you're doing the derivative of this, it's going to be a little complicated over here because you have to use the chain rule, but more than that, you have to view this as 1 plus 2x to the power of minus 1. You see, 2x to the minus 1. And then here, you're looking at d over dx, x to the power of minus 1. When you do the derivative of this, you'll get a minus 2x to the minus 2, which will be minus 2 over x squared. That's just this part right here. And then this ln u will be 1 over u, and that will be 1 plus 2 over x. And then this right here alone will generate minus 1 over x squared. So you have to channel all of this out in your calculations. But you keep this as is and just flip this around. Watch what happens. Minus 2 over x squared over 1 plus 2 over x. This is still all the numerator part right over here. You're flipping the denominator now. Times minus x squared over 1. You can cancel this x squared with this x squared, this minus with this. So what you end up left with is this 2 on the top and this 1 plus 2 over x, all to the x equals infinity. When you run x equals infinity, this zeroes out right over here. Because 2 divided by infinity is exceedingly small number, you get a 0. You end up getting 2. But your final answer is not 2. You have to factor this in. Y is equal to e to the power of 2, and that right there is your final answer. And then you will be done. So up till now we've looked at the basic indeterminate forms for which you had 0 over 0 or the infinity over infinity form appearing, and we could use a basic LHopitals rule. Then we've also looked at indeterminate product types, and we've looked at the indeterminate power types. Now the only thing that remains are the indeterminate difference types, where you have an infinity minus infinity playing out. If you look at this function before you and you put 0 in places of these x's, you end up with an infinity minus infinity form type, and you basically have to convert this by some means into a quotient formation so you can get into the basic LHopitals type of indeterminates. I would not recommend proceeding as this. And when I talked about the indeterminate forms, I said you can use one of 3 different types of techniques, such as factoring or isolation. You can do common denominators or rationalizing to get this into a quotient form, and that's what you should do. Look at these at their individual function types. You'll get 1 over sine x over here, and you get minus cosine x over sine x. So suddenly your question looks like this. When you put zeros in places of this, you get 1 over 0 minus 1 over 0, and you're dealing with this type of form. And you're on the right track. You have to do the derivative of this limit expression before you. And when you do the common denominator, you have sine x over here. In the numerator, you get 1 minus cosine x. When you have done it this way, now look at what happens. And you put the 0 over here. In places of these x, you get 1 minus 1, which is 0 over 0. You see, we've converted this into a 0 over 0 type, for which the basic LHopitals technique works. You do the derivative of the numerator and derivative of the denominator, and that enables you to put in your actual value. 1 minus cosine x and sine x. When you do these derivative procedures over here, at the end you'll be able to put 0 in place of this and get to your limit. The derivative of 1 minus cosine x, you can imagine, will be positive sine x. And you can run that through yourself. It's something you can do it in your head, and this will be cosine x. You can put x equals 0. When you do that, you get a 0 over 1, and you get a 0, and you're done. So essentially you are able to use a good technique over here for an indeterminate type of expression where you have an indeterminate difference over here, a difference of infinities at play, and you do that by converting it to a quotient form and proceeding that way. For this question over here, we have another difference, f and a g, a difference expression, an indeterminate difference. If you put a 0 in places of these x's, you'll get infinity minus infinity at play. Infinity minus infinity. So you have to do some sort of technique. I would here proceed with a common denominator and go with that way. I would not do a cotan x over 1. I would not view it as this. I would break this cotangent into its base function. So I would rewrite everything as this. Limit as x approaches 0. I have cosine x over sine x. That's how I would do it. Minus 1 over x. If you do it the other way, you can find out you'll end up down a path where you still cannot determine a good limit. By breaking this cotangent into this, you can end up with a better result. You do the common denominator over here, you have x sine x. Here in the numerator, you'll have x cosine x minus sine x. Now you're going to be doing the derivative procedure of this in the numerator and in the denominator. And you can do some of these things in your head. If you do the derivative here in the numerator, you have a product rule, and you have an individual expression here in the denominator, you have a product rule at play. You can do all of this and come up with the result. In the numerator, this minus sine x will become a minus cosine x. This part over here will become a cosine x minus x sine x. In the denominator, you'll get here a sine x plus x cosine x, and this allows you to put x equals 0, but sometimes you have to see if you can even do that, let alone. Anyhow, when we come back to this expression right over here, if you were to put zeros in places of these x's, you'd get, in place of this expression over here, you'd get the 0 over 0 form, so you're in the right path. If you were to put in this form, you get 0 over 0. So you've converted something which looks like this into something which looks like that by means of a common denominator. Anyhow, We look over here, the cosine x's cancel out. You end up with a minus x sine x divided by sine x plus x cosine x, and you can put x equals 0. But before you put x equals 0, you should test. When you do your test over here, you put zeros in places of these x's. What happens? You get a 0 in the numerator and you get a 0 in the denominator, so you're still looking at this form over here. That means we're not good enough yet. We have to do another round of derivatives. Remember, with the LHopitals rule, you can do multiple rounds of derivatives until you're satisfied. We do the derivative here, the numerator and the denominator, and we see what expression we end up with. When we do the derivatives here, we have a product rule at play, and we would end up with the following expression. We would have minus sine x on the top, and over here we would get a minus x cosine x. In the denominator, when we do all of this, you have a product rule here and an individual item over here, you get a cosine x. Here we would get a, I'm just doing this in my head, plus cosine x minus x sine x. When we combine all of these terms, we get minus sine x on the numerator minus x cosine x. In the denominator, we can combine these two terms right here. We get 2 cosine x minus x sine x. Now we can put x equals 0, and this should be where we end up with our final answer. Put zeros in places of these x's. In the numerator, you'll get sine of 0 as a 0, minus 0 times that is a 0, which is fine. You can have zeros in the numerator. Put it in the denominator. This zeroes out. 0 times sine of 0 is 0. 2 times cosine of 0 is a 2. 2 minus 0. So we're ending up with 0 over 2, which is a very relevant answer because we end up with a 0. You can do a numerator 0 divided by denominator a number, but you can't do it the other way around. So this answer right here will be good. So our video for today for this subject will end with this last question. I know this has been a long and has been a difficult and a conceptual video, but that's the topic of indeterminates. They're just not easy. When you're looking over here, you know you're dealing with a difference over here, an indeterminate difference of functions. You have to do a common denominator. Before we do anything, we'll do a common denominator here. If actually you even put in ones over here, you get a 1 over 0 minus 1 over 0. You're dealing with this type of form, infinity minus infinity at play. That's an indeterminate difference form, and we don't like that. We have to convert that into some sort of quotient form, 0 over 0 or infinity over infinity. So for this question, we know we're dealing with an indeterminate difference of infinities, infinity minus infinity. We'll do a common denominator. What's the common denominator? X minus 1 and ln x. It'll be just ln x times x minus 1. X minus 1 goes in this ln x times, so you'll have ln x and this x right here. Here ln x goes in this x minus 1 times, you'll get x minus 1. When we open this up, we'll get x ln x minus x plus 1 over ln x times x minus 1. That's our new limit expression. Now if you put 1s in all of this, if you literally do put 1s in places of this, you'll see in the numerator you'll 0 out, in the denominator you'll 0 out. So we've converted that indeterminate differences, infinity minus infinity, to a 0 over 0 form. The ideal form in such situations, 0 over 0. So when we come up to this expression over here, which is just all of this initial part being reconverted into something which is a 0 over 0 form, now we have to actually do the basic LHopitals rule. We'll do the derivative of the numerator items and derivative of the denominator items, and that'll be a little bit of work, but that's fine. We're doing the derivative procedure over here. When we do the derivative here in the numerator, we're going to have a product rule which will come into place, and in the denominator again we'll have a product rule which will come into place. It'll be a little bit of work, but we can get away with that. Now let's do the actual derivative over here. Let's look at this x ln x. We'll basically have ln x plus x times the derivative of ln x will be plus 1. Derivative of minus x is a minus 1, right? Here in the denominator, we'll have x minus 1 times the derivative of natural log x, which is x, plus natural log x times the derivative of that is just going to be natural log x, and we can do x equals 1. Let's simplify what we have over here. We have natural log x over, we have x minus 1 or x plus ln x, and that should technically allow us to put 1 over there. When you do put 1 in places of this, you're zeroing out the numerator and you're zeroing out the denominator, so you're still having a 0 over 0 expression, which means you're still not done yet. You have to do more derivatives over here. You have to bring everything down into a derivative form for a second round. We'll do a second round of derivatives in the numerator and second round of derivatives in the denominator, and we'll see how that plays out. When you're doing a derivative here in the numerator, we'll get a 1 over x. When you're doing the derivative here of this entire expression, you can see this is a little bit of a quotient rule here at play, and this right here is a separate item, which is just a 1 over x. We have to do this derivative of x minus 1 over x. We can do that right here on the side and bring the expression over here. Quotient rule over here. We'll have x times the derivative of x minus 1, which is just a 1, minus x minus 1 times the derivative of x, which is just a 1, divided by x squared. And what do we get over x minus x plus 1 over x squared? We get a 1 over x squared. That's what I'm getting here, 1 over x squared. The derivative of this entire part right here simplifies to 1 over x squared. So we're good. Remember, we are having to do a second round of derivatives here, because here in this step we were still getting a 0 over 0 indeterminate form when we plugged in a 1. So that told us we're not ready yet. We have to do another round. Now when we come over here, we can simplify all of this algebraically. We have 1 over x in the numerator, which came from the derivative of natural log x. We can do a common denominator here. 1 over x squared plus 1 over x, the common denominator is x squared. 1 plus x. You see all of this? 1 plus x. Everything you can do here on the side on your paper. Flip everything around. 1 over x times x squared over 1 plus x. X equals 1. Now we're so close to being done that I can feel it. You can cancel this x out with this x squared. I end up eventually with my final expression of x over 1 plus x, where I can still have the luxury of putting x equals 1. And when I do, I get a 1 over 2. 1 over 2, and that brings me to my final concluding result. So the limit of this entire function right over here, as x approaches 1, is equal to 1 over 2, and it looks like a good answer to me. It's going to be a right answer. And how did we go about doing this procedure? As a rehash, we looked at this, we found a common denominator. When we found the common denominator, we just simplified the expression algebraically, and that became our new limit. Up till this stage over here, from this stage we were at infinity minus infinity indeterminate form. When we brought it into this form here, we were now at 0 divided by 0 indeterminate form, the quotient form of indeterminates. Then we ran it through the LHopitals rule in the numerator and in the denominator, and we got to the first round of results, and we noticed we're still at that 0 over 0 form, and it's not good. So we ran it through a second round of derivatives. When we ran it through a second round of derivatives, derivative in the numerator, derivative in the denominator, running it through algebraically to a final simplified expression, and then we plug in our limit x equals a value of 1, we come up to our final result. So remember, for this indeterminate type of differences, the infinity minus infinity, you're using some sort of quotient procedure, but end result of a quotient procedure by means of some sort of rationalizing common denominator or factoring, such that you can come up with this form 0 over 0 or infinity over infinity. Then you can run it to the basic LHopitals procedure of finding a limit. So keep in mind everything we've talked about. Indeterminate forms of the 0 over 0, infinity or infinity type, which are the basic forms. And we talked about the indeterminate product types. We also looked over at the indeterminate power types and at the indeterminate difference types. From all of these, in my opinion, these difference types questions are the hardest, because to convert an initial expression by means of either rationalizing, common denominator, or isolation, such that you can get into a quotient form, is, in my opinion, the hardest aspect of these types of questions. I hope you enjoyed this video. I understand it was difficult, it was lengthy, it was conceptually difficult, but this is the topic of indeterminates. They're just not easy. Feel free to view this video as needed. You might have to refer back to it several times. Stay tuned, because I have many more videos on the way. Thank you for watching. Have a nice day. Bye.